So hey everyone, my name is Jeff Zemerick, and my colleague and I, David Smithbire, have been working on putting together on AWS a way to do full cycle model training and serving. And we wanted to share that with the community. So happy to be here today. So just a little about me, the introduction, same stuff there, cloud architect, worked with AWS about 12 years, current chair of the Apache OpenNLP project, and DevOps engineer. Got to keep my hands dirty sometimes. Located outside Pittsburgh, I would say in the snow, but it seems like it's snowing everywhere, but it's still snowing. My colleague David Smithbire, we work together at a consulting company called M&S Consulting. The link is down there at the bottom. He's also a cloud architect in AWS about the past 5 years. He really likes containers and Kubernetes and that type of DevOps work. And he's in Morgantown, West Virginia. I think he's in the chat. So maybe if there's any questions, he can help give me a hand there. So the goals for our project, when we set out what we wanted to achieve, is that we wanted to have an architecture managed by Terraform that would allow us to train NLP models and then serve those models, because a model that's trained is useless without being served and made available to the world. And we wanted this architecture to be automated, needs to entirely be able to go on its own. It needs to be scalable because we don't want to just train one model at a time. We want to have a pipeline of models continuously going through being trained and made available for production. And lastly, extensible. We know that our solution is probably not 100% your solution, and our solution today is probably not our solution tomorrow. So we wanted it to be able to be modified to fit different use cases now and in the future. Down at the bottom, just an overview of what we're working toward. We have our model parameters and our training data. They're going to feed into training our model, where the model is trained and evaluated. Once done, the model is published. The model could be served and accessed by an HTTP client over a REST-like interface. So crash course NLP. NLP is not at all required. You don't have to be an expert. It just kind of helps to know what we're going after here and what the end goal was, if you have a little basic understanding of some of the terminology. So what we're training here today is an NLP named entity recognition model. And this model allows us to identify persons' names in natural language text. So in our sentence there, George Washington was president. George Washington is read because we want our model to be able to say, hey, that's George Washington, he's a person. And if you're not in NLP or even tangentially, this type of model is used everywhere in the world today, pretty much. So a lot of use cases for it. And like I said, good news. You don't need to be an NLP expert at all. The past couple of years, there have been great leaps in NLP technology. And I argue that one of the most important leaps was the democratization of that technology. Back when I started getting familiar with NLP about 10 years ago, I found it very obscure. It was very niche, and it took a lot of legwork to be able to get something working. And today, thank goodness, it's the complete opposite. There are a lot of good frameworks out there that you can jump right in with little experience, and you don't need that vast domain knowledge. So it's a great thing to experiment and play with without feeling like you have to be an expert. So the cloud infrastructure that we're going to make, that Terraform is going to manage for us, is kind of divided into two sections. The first section is the base infrastructure and the model training. And this left column is the long-lived AWS resources, the things that will live there forever. And then the right side is the model serving. And so those are the short-lived AWS resources. Intend to be short-lived. Models get replaced and so on frequently. So they may run for a little while, but they're not intended to be run forever. And so we're going to use Amazon Event Bridge, To kick things off, we're going to do our training on Amazon ECS cluster. We're going to be able to queue up models for training using SQS, use DynamoDB to store our model metadata and the status of our model so we know where we're at. Our Lambda is going to kick off our model training, and Amazon S3 is going to hold all of our generated models and their artifacts. And of course, everything then lives in Amazon VPC, which probably doesn't even really need mentioned these days. And on the flip side, our model serving is going to be an ECS service and tasks, and they will be behind an application load balancer. So nothing extremely obscure or groundbreaking, but the assembling of the pieces is the important part and the hard part. And in the little graphic there, just showing the components, the infra at the bottom, and how training and serving sit on top of those. So the VPC and the ECS cluster are the ones that everything sit up on. So now putting those AWS services, a picture kind of to their process in that same diagram we saw earlier, trying to just give you an idea of the big picture of things here. So our model training parameters will go into an SQS queue. And from there, they will be consumed by an Amazon Lambda function. That Lambda function will pull from that queue to see what model we want to train. And the Lambda function is triggered by an Amazon Event Bridge rule that fires every 1 minute in our code. You might want to raise that. For yours, depending on your needs, 1 minute was pretty good for testing. But the Amazon Lambda function will fire every minute and see if there's anything on the queue, models to train. If there is, it puts a record into our Dynamo table about that model and then kicks off the model training. And it does that by starting a task in ECS with our model parameters. Launches our Docker container, trains the model. Once it's trained, that model's evaluated, and we have a loop here. If we want to go back, we can and train and evaluate. Then we publish the model to S3. So the model artifacts, just the files, the model file itself, and the other things that get generated along with it go to S3. And then to serve the model, we're back to ECS, our same ECS cluster. We just launch a task in ECS to stand up a service and make it accessible to the world through a load balancer. And so then we can hit it with curl or any other of your favorite HTTP clients for testing. So the other technologies that are not AWS are also very important in this. And the first one is Flare NLP. It's an open source NLP library, deep learning built on top of PyTorch. It's available on GitHub. It's a really good introductory or beginning NLP library. It's one of those that I mentioned before. Doesn't require vast amounts of knowledge to get started with. You can pretty much take their examples that they have in their project and adapt them to your needs and have working stuff. So highly recommend it for everyone, especially to those who may just be getting interested in NLP. Our Docker containers for training and serving our models. As you would expect, since we're using ECS, the model training and serving are defined by Docker containers. Those images get pulled down when needed. Our Lambda function is written in Java, Java 11. You need Maven to build it. You could use any language you want. Java is my personal go-to. So it was an easy choice there for me, but you can use any of the Lambda supporting functions, languages, sorry. And lastly, what would a project be if it didn't have some bash scripts thrown in? So we got some bash scripts in there that facilitate kicking off a model and doing some tests. So our containers that do the hard work, they're the heroes of it all, really. There's two different ones, training and serving, two different Docker files. Screenshot there from our GitHub project, serving directory and a training directory. And they each contain their respective Docker file for you to go to build on. So these containers are built on the CUDA image of Universal Base Image 8. It's a real good image for this type of work. It's got the CUDA dependencies. If we want to do GPU training and runtime on GPU, but also if we don't have GPU, it'll fall back to CPU seamless. So unless you know you're not going to use GPU or never in the future, then you can use a different base image. But if you think you might use GPU, and these are good base images to start with, because you save yourself some work in the future. The two Docker files, if you take a look at them in GitHub later, they're very similar. You could probably make a pretty strong argument that you could combine them into a single Docker file, or maybe if you didn't want to go that far, at least abstract out the commonalities into their own base image. The Python stuff and a few dependencies are common across both. So you could do some simplification there if you want to. We didn't here for this, mainly just because good learning purpose and get you familiar with what's in there. Now, these images are large, be forewarned, due to the CUDA runtime and due to PyTorch, they are rather large images. Just be aware. So first steps is to build and push those Docker containers, the images up to your repo of choice. Then we'll build the Java Lambda function, edit the Terraform variables that we have a screenshot there on the right, the prefix, the region, the AZs, typical stuff that you would set. And then lastly, most importantly, is to get excited. I have factual evidence that if you're not excited, it won't work. So you have to be excited before you run Terraform live. And then once you do that, your ECS cluster will be built. You'll be able to see it in Amazon. Typical stuff, nothing too amazing there. And so once we have our ECS cluster up, we're ready to train the model. So to initiate the training of a model, we send off a message to our queue. And this bash script in our repo facilitates that for us. So it gets the queue URL from our Terraform output, takes in a model name. If you don't give one, it just defaults to my model, and then uses AWS CLI to just publish that message up to the queue. The one important caveat there is be sure just to export your Docker Hub username or wherever you pushed your Docker images to. Otherwise, your ECS task will fail, and you'll wonder why. That one gets me. I probably should add a check in there for it. Just be sure you do that first. And you'll notice that the message body is just a JSON message. And these are just the parameters that we're passing in to tell it what kind of model we want to train, the name of the model, the Docker image that we want to use to train it, and our embedding. So you can see here that we just picked a few of the parameters, but there's a lot of room here for the extensibility that I mentioned before. If you want to put in other parameters, if you want to customize stuff, this is a really good place to add to the parameters that go into the Docker image or to the training itself. So after that, once we got the message published, our trusty Amazon event bridge rule every minute will trigger our Lambda function. And the Lambda function will look at the queue and see if it has any work to do. If it consumes a message, it'll read that message, deserialize the JSON into a Java object just for convenience. And then it'll create a task on ECS with those parameters to train our model. And if all that goes well, then it inserts the model metadata into a DynamoDB table. So at this point, if you look at the Dynamo table, you'll see that the model is in the in progress state, and you'll have the model name and other information about it. And once the model training is done, it's uploaded to an Amazon S3 bucket. I'm not sure if I mentioned earlier, but the model training based on your parameters and stuff can take a long time. So just be forewarned that it could be a long adventure there for it to train. So for testing, you can lower some things for proof of concept to see it go end to end, but otherwise expect a good while there. There's the Lambda function that I mentioned. It consumes that JSON message, and the code on the right is just the POJO of that message. So again, a really good place. So we got the name, the epochs, embeddings, and the Docker image. A really great place if you want to put in other parameters that you want to tailor the model training with. You know, if you're somewhat familiar with deep learning, you know that there's a lot of hyperparameters that you can tinker with. So this would be a good place where if you want to put more in or change them to do it. The trained model artifacts, once it's done, they get uploaded to S3, and these are those files here. And for this one, I just did one epoch because I wanted it to be quick, just to get it through the process. And so you'll see a best model, a checkpoint, and a final model. And those three files are all the same file. They're all written at the end of the first epoch. So that is our actual model file. Then you have the training log that contains all of the information that was captured during training. And the output of that training log also goes to standard out, which is captured by CloudWatch logs. So if you ever need a history of how the model trained or some of the values during training, you can check the CloudWatch logs for the ECS task, and you'll find it in there, or the S3 bucket, either one. So our Dynamo table, it just gives us a high-level view of what's going on with our model training pipeline. So whenever a model changes its state from pending to in progress or completed, the table will be updated. It's pending when Lambda consumes it from the queue before it starts the task. And then once it starts the task, it goes to in progress, and once it's done, it's completed. And so it's just a way to have a high-level view of what's happening, when did models start training, and what they're up to. So our Terraform files, how we actually implemented it, are divided into two separate Terraform directories. That's the infra, which we saw earlier, manages the low-level stuff, the stuff that sticks around for a while typically, the VPC, routes, subnets, security groups, that sort of thing. It also manages the ECS cluster. Since we're sharing the ECS cluster for training and serving, the ECS cluster sticks around as well. It also manages SQSQ and Lambda Function, Event Bridge, and any other resources that it needs. And then the other directory, the serving directory, those Terraform scripts build upon the earlier resources to make a model available over HTTP. So it uses the same ECS cluster, the same VPC, same route, same subnets to expose that model. And I should say that the infra resources are meant to be long-lived, but they don't have to be. For example, if you wanted to just spin this up to train one model and then tear it down at the end, that's perfectly acceptable. So the model training, we got those two separate directories for the infra and the serving. And we do have to communicate some values between those templates. So when we go to serve a model, we know what ECS cluster we're going to use, or we know the name of the S3 bucket containing the models that were generated. So to facilitate that communication between the two templates, we use EC2 parameter store. So our infra Terraform scripts will put those values into parameter store, and our serving scripts will then be able to read those values from parameter store. Now, there's probably a lot of other things you could use here to facilitate that communication. This one seems to work well, and it also provides a good decoupling between the serving and the infra scripts. They aren't tight. You could run multiple serving stacks if you wanted to without issue. So logging is very important during any type of system, especially when you're training a model. Always need logs. So it's configured that all logs from the ECS task and the Lambda function go to CloudWatch logs. And between those two, you get a real good insight into what's happening. If something went wrong, you'll find it in one of those two places. Also have container insights enabled to give us a better look at what memory you're using. Perhaps if you could benefit from a larger EC2 instance. I ran these on a T3 large, so not a real big instance, but it could have benefited from more resources. So it just gives you an idea of what's happening. And I've said earlier that model training can take a long time. So having those logs throughout the process is even more valuable. Some notes, you could call them lessons learned along the way. things run into, is that training a model, the task on ECS is best suited by using the ECS run task API. The run task API is intended for batch jobs that perform work and then stop. And that's exactly what model training is. It does its model training and then it stops. Previously, looked at, before I got super familiar, looking at the other ECS APIs, it's not services, because you only need one. So use the run task API. And that also allows you to have multiple concurrent tasks on the same cluster. So if you wanted to train in models at the same time, as long as your EC2 instances or your in your ECS cluster have the resources available, then you can absolutely do as many as you want. Model serving. So once we have a model and it's up in S3, it doesn't do any good just sitting in S3. We want to be able to use it to apply it. So in our Terraform scripts, you just need to edit the variables file to set the model name. And this is the same name that you gave the model when you kick training off. So you just give it that same name. And the Terraform script will start, it'll reach out to parameter store, get the values it needs about the ECS cluster, and it will create the service and the tasks to serve that model. It'll also create an ALB in front of the ECS service to give you an endpoint to hit. So in the example that I copy and pasted here, just do a curl post to the ALB, and the path is NER. That's in the Python script that runs the NLP. And you just give it data, text in the body of the request. My classic example, George Washington was president. And the result there is JSON saying that text George Washington was tagged as a person with a score of about 84%. And then it gives you the character indexes 0 and 17 of where that person is in that text. So we have gone from taking training data through our pipeline. We trained our model. We did the evaluation, captured in the logs, pushed the model to S3. And now we are making the model available to ourselves, to the world, and to wherever it needs to be. And I would like to say that there are a lot of other ways to do what I just described. When you look at clouds and technology, you see a pile of Legos, and we built a house out of those Legos. And if I gave you the same Legos, you would build a different house, but it would still be a house. So I don't want to imply this is the only way to do it. There are a lot of other AWS services that you could have used, or different cloud services, native or not, that you could have used and got the same result. So a few questions asking myself as I went. Why didn't you use SageMaker? Amazon has a managed service for it. Why didn't you use it? It just comes down to a balance of control versus an all-in-one managed service. For something like this, where we're building it for ourselves, having that control is nice. We may decide later that a managed service is better, or we may not. We may find that the managed service needs things it doesn't have, and so we stick with our own. So it's just a balance. We did not use any existing Terraform modules. There's a lot of great ones out there. It would definitely simplify the code. Did not use them mainly just because learning experience. You put together yourself, you learn, in my case, I learn a lot more than what I otherwise might have by using some pre-made modules, especially finding the gotchas in there. You find those a lot quicker instead of ones that people have found before you. And why not use AWS Fargate? Simplify the container management there. And the reason is that Fargate does not currently support GPU. So if you want to do GPU training, you have to use ECS. Just grab you an ECS optimized AMI that supports GPUs and launch you a GPU instance, and you're off to the races. And some other questions: why did you use Flare? So earlier, it's a great NLP framework just to start with. Why did we separate the training and serving Terraform directories? to allow separate life cycles. Models that are trained, the life cycle for model being trained and the model being served are different. Want to keep those loosely coupled, allow them to exist separately. We have a variable called name prefix, and you might say, what is that for? And that's just to allow for multiple concurrent instantiations. So if we wanted to use these same Terraform scripts to fire up multiple ECS clusters in the same Amazon account, just give a different prefix, and all the resources that it creates will have that prefix. So you don't limit yourself to just one. What happens if an ECS model training task cannot be started? Maybe the cluster is at capacity. There's no more room for our resources that we want. The request just stays on the queue, and that's the whole point of the queue. When one model training is complete, another one will be able to be started once it gets consumed again. And what happens if a container becomes unhealthy? If you take a look at the code in the Python, you'll see a health endpoint, and it just returns HTTP 200 OK. And so if for some reason it doesn't return that, it can't be reached, the ECS service will replace that model, that container. So there's a ton of stuff here left to do. It's definitely a solid foundation for our needs and going forward, but there's still a lot. One thing that would be nice that we'll be working toward is having automated quality gates, just some simple regression testing essentially on our models to make sure that the new models meet the quality standards that have been set by the ones in the past and by our organizational requirements. Then make model serving accessible by friendly DNS names. If you have a domain name, the load balancer names can be kind of obscure. And lastly, parameterize security groups. If you do check out the code and you run it, just be aware that for the purposes of this presentation, the code, the model and stuff, the model itself, and I think the cluster is open to traffic from anywhere. So you just want to lock those down before you actually deploy it for real use. So here's the code. I'll have these slides up for you to get or to refer to. Be happy to help if you have any problems. Just follow the steps in the README. It all works as described here. Build and push the images, build the Lambda function, Terraform apply, and then enjoy your success and take off early and go home, and because you did enough work there for one day. And thank you. That's it.